Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll continue with some numerical examples on torsion of shafts. Let us start with the first example. A solid circular shaft has to transmit 80 kW at 200 rpm. The maximum torque is likely to exceed the mean torque by 18%. Find the minimum diameter of the shaft required if the angular twist is limited to 1.2 degree in a shaft length of 3 meter. Given G is equal to 85 gigapascal. So the shaft has to transmit a power of 80 kilowatt at 200 rpm. While transmitting the torque, the maximum torque is likely to exceed the mean torque by 18%. When this maximum torque condition is given, you should take that torque value, that maximum torque value, into the design of shaft. Because momentarily also, if the torque increases, that will increase the shear stress induced on the shaft, and you should design the shaft for this maximum torque. Average torque transmitted you can find out from the equation P is equal to 2 pi nt divided by 60,000. So the maximum torque is 18% more than that mean torque or average torque you are getting by that equation. So maximum torque is 18% more than the mean. So you can multiply that mean torque, whatever mean torque you are calculating, that you can multiply with 1.18. So you should design the shaft for this maximum torque. Now you should find out what is the minimum diameter of the shaft required if the angular twist is limited to 1.2 degree in a shaft length of 3 meter. Only angular twist is the constraint. We are not restricting the shear stress. We are more bothered about the angular twist undergone in the shaft, and we should limit that angular twist to 1.2 degree in a shaft length of 3 meter. And you are given the modulus of rigidity of the shaft G as 85 gigapascal. Length is equal to 3 meter or 3000 mm. Modulus of rigidity G is equal to 80 gigapascal or 80 into 10 raised to 3 Newton per mm square. First we will calculate the mean torque. The mean torque is P by 2 pi n into 6 into 10 raised to 7 Newton mm. Now power transmitted is 80 kilowatt, so you have to substitute in kilowatt only. 80 kilowatt. RPM is 200. So substituting that, you will get the mean torque as 3.8197 into 10 raised to 6 Newton mm. Now after getting this, you need to find out the maximum torque. So maximum torque, as I mentioned, you can multiply with 1.18. What is given is maximum torque is 18% more, that is mean torque plus 18% of mean torque. So that is 18 by 100 or 0.18. So T mean plus 0.18 T mean, that is the maximum torque, or T mean into 1 plus 0.18 or T mean into 1.18. So when you say 18% more means you can multiply that mean torque by 1.18. If it's 20% more, you multiply with 1.2. If it is 5% more, we just multiply with 1.05. Okay, not 1.5, 1.05. So here if you multiply with 1.18, you will get maximum torque as 4.5073 into 10 raised to 6 Newton mm. So this is a maximum torque transmitted by the shaft. Now you have part of torsion equation. T by J, we studied T by J is equal to tau max by R is equal to G theta by L. Since angular twist is the constraint here, so you have to equate T by J to G theta by L. So if a shear stress is the constraint, T by J you should equate to tau max by R, or T is equal to J by R into tau max. So here T by J is equal to G theta by L. So this part of the torsion equation you should take to find out the dimensions of the shaft. So from this equation you can rearrange and get the polar moment of inertia. J is equal to TL by G theta. Okay. Torque is known, maximum torque which we calculated you have to substitute. Maximum torque is 4.5073 into 10 raised to 6 Newton mm. Length of the shaft is 3000. G is modulus of rigidity 85 into 10 raised to 3 Newton per mm square. Theta is given as 1.25 degree in a shaft length of 3 meter. 1.25 degree means 1.25 into pi by 180. You should always use radian in this equation. So theta should be in radians. So to convert into radians, multiply with pi by 180. So it's 1.25 degree and converted in radians. Now calculating this, you will get J as 7.596 into 10 raised to 6, and that J for a solid shaft is pi by 32 d to the power of 4. So you can equate this as 7.596 into 10 raised to 6 is pi by 32 into d to the power of 4. Solving this, you will get the diameter as 93.79 mm. So much is the diameter required to restrict the angular twist to 1.25 degree in a shaft length of 3 meter, while the shaft transmits 80 kilowatt at 200 rpm. So minimum diameter required is 93.79 mm. So you can use a higher diameter, so that will always reduce the angular twist, but you cannot go below this. And we are not checked that maximum shear stress, so we are more concerned with the angular twist for this particular application. So this is a minimum diameter required to restrict the given constraint. Now let us work out another example. A solid circular shaft has to transmit 300 kilowatt at 120 rpm. The maximum torque is likely to exceed the main torque by 9%. If the maximum shear stress is limited to 40 megapascal and the angular twist is limited to 1.8 degree in a shaft length of 5 meter, find the minimum diameter of the shaft required to satisfy the above constraints. Given G is equal to 80 gigapascal. In this problem, the power transmitted is 300 kilowatt at 120 rpm, and again maximum torque is exceeding the main torque by 9%, and the maximum shear stress is limited to 40 megapascal. So shear stress is also a constraint here. Maximum value of shear stress is limited to 40 megapascal while transmitting this power, and also angular twist you should restrict to 1.8 degree in a shaft length of 5 meter. In every 5 meter, the angular twist should be 1.8 degree. In 10 meter, it can be 3.6 degree, but in 5 meter, you should restrict to 1.8 degree. This is a constraint. So there are two constraints. Maximum shear stress should not go beyond this. Angular twist should not go beyond this in 5 meter length. And you are given the modulus of rigidity is 80 gigapascal. So these are the given data. Power transmitted 300 kilowatt, rotational speed at 120 rpm, maximum shear stress 40 megapascal, angular twist 1.8 degree. It's in a shaft length of 5 meter or 5000 mm. Modulus of rigidity is 80 gigapascal or 80 into 10 raised to 3 megapascal, and Tmax is 9% more than the mean torque, so 1.09 into Tmean, that will be the maximum torque. Now in this problem we have to find out the diameter of the shaft separately for satisfying this constraint as well as angular twist constraint. So two constraints are there. Separately find out the diameter of the shaft to satisfy both the constraints. So let us first calculate the mean torque and maximum torque transmitted by the shaft. So this is a formula to be used. Power is given as 300 kilowatt. Directly you can substitute in kilowatt in this formula. N is 120 rpm. So substituting that, you will get the average or mean torque transmitted as 23.873 into 10 raised to 6 Newton mm. Now to find out the maximum torque, you can multiply this with 1.09, because maximum torque is 9% more than the mean torque. Because it's a 9% more, you have to multiply with 1.09. So this multiplied by 1.09, you will get 26.0218 into 10 raised to 6 Newton mm. So this is the maximum torque transmitted by the shaft. On an average, this is the torque transmitted, and sometimes the maximum will go to this value. So we have to find out the diameter of the shaft to carry this torque. You have to find out the diameter of the shaft taking this torque into consideration. Now let us go for the first constraint, shear stress consideration. So you have to find out the diameter of the shaft by taking the shear stress consideration. So one part of the equation is T is equal to J by R into tau max, or T by J is equal to tau max by R. That is one part of the torsion equation. So rearranged form is T is equal to J by R into tau max, and J by R is polar modulus, and for a solid shaft it is pi by 16 d cube. So you can always write for a solid shaft T is equal to pi by 16 d cube into tau max. The maximum torque which you have obtained, you can substitute here, and maximum shear stress should be limited to 40 megapascal. So for keeping that maximum shear stress to 40, you should have minimum diameter as 149.079 mm. So this is a minimum diameter required for the shaft to keep the maximum shear stress to 40. When you use this diameter, you will have a maximum shear stress 40 megapascal while transmitting this torque, or while transmitting 300 kilowatt at 120 rpm. So this is one of the solution for the diameter. Okay, one solution for the diameter to satisfy this constraint. We need to check the other constraint and decide about the diameter. So other constraint is angular twist consideration. So another part of the torsion equation is T by J is equal to G theta by L. Now from this you can find out J. J is equal to TL by G theta is equal to 26.0218 into 10 raised to 6. That is a maximum torque, into length is 5 meter or 5000 mm. G is 80 gigapascal or 80 into 10 raised to 3 Newton per mm square, and angular twist is 1.8 degree. Okay, that is in a shaft length of 5 meter. So you have to convert into radians, 1.8 into pi by 180. Substituting that, you will get J as 51.7687 into 10 raised to 6. Now equating that J to J is polar moment of inertia. It is pi by 32 into d to the power of 4. So J is 51.7687 into 10 raised to 6. Substituting the value of J, you can solve for diameter. So from this you can solve the diameter as 151.536 mm. So this is a minimum diameter required to restrict the angular twist to 1.8 degree in a shaft length of 5 meter. So this is another solution to satisfy only the angular twist constraint, and the previous one we got for restricting the maximum shear stress to this value. As I mentioned, you can increase the diameter but should not go below this. Okay, so it can be more than 149.079, but if you increase, this shear stress will decrease. So increasing this value for this torque to be transmitted, increasing the diameter will only decrease the shear stress. So you can increase the diameter, but it should not go below this. So it can be more than 149.079. In this case 1.536 mm you are getting. You can increase the diameter, but increasing the diameter angular twist will decrease, but you cannot go below this. If you decrease it, then angular twist will increase. If you decrease the diameter, polar moment of inertia will decrease and angular twist will increase. The cross section will become weak if you decrease the diameter, and it will undergo more angular twist. So you cannot decrease the diameter less than this. So out of these two values, say you have one solution here 149 and here 151. Out of these two values, now which diameter you should use? You should always use maximum diameter as the minimum required diameter for transmitting this power while satisfying both the constraints. So you should keep maximum diameter as the minimum requirement, minimum required diameter. Even though the question is asked to find out the minimum diameter to transmit the power, out of the solution obtained, you should take the maximum value as the minimum requirement. So out of the two diameters, you take this as the solution for the problem. So minimum required diameter for transmitting that power is 151.536 mm. So if you are keeping this diameter for the shaft, both the constraints will be satisfied. When you use this diameter, angular twist will be limited to 1.8 degree in 5000 mm length, and shear stress will be less than 40 megapascal. It will not reach 40 megapascal. It will be less than 40 megapascal. That's all for today. Thank you for watching.